All right, so today we're going to talk about the other half of this vegetation chapter. So basically, we're going to talk about a set of vegetation indices that we can use for various applications. So it's kind of like a rich toolbox, and will give you a set of tools for different applications. So the vegetation indices are the extract and model various vegetation biophysical variables using remotely sensed data. So these kind of indices are usually dimensionless, which means that they use different band equation and they can cancel the up unit and low unit, so it's usually dimensionless. And radiometric measures that indicate relative abundance and activity of green vegetation. For example, a lot of vegetation index like NDVI or racial index can be used to represent how well does the plant's growth. And typically, also throughout the entire vegetation growth cycle, you can see certain curve that can be characterized by these kind of indices. So it provides maximized sensitivity to plant biophysical parameters and also normalize or model external effects such as sun angle, viewing angle, and atmosphere for consistent spatial and temporal variations. This is often refers to various options to reduce the atmospheric or background impact on the index, and also normalize internal effects such as canopy background variations, including those topography like slope and aspect, or soil variation and differences in woody vegetation. And also be coupled to some specific measurements, measurable biophysical parameters such as biomass, LAI, and APAR as part of the validation effort and quality control. So the tool that we introduced in this chapter is very important. So the most simple one, the first one is simple ratio, which is SR. So basically provide value information about vegetation biomass or AAI, especially in high biomass vegetation such as forest. What this means is that this kind of index can be in a certain way correspond well to biomass or LAI. For example, when they grow in the later stage, then when biomass or AI increase, typically you will also see simple ratio increase as well. So especially in high biomass vegetation, I think this is like characteristic compared to the NDVI, which the later one, NDVI have a saturation problem in the high biomass region, but SR seem like not having this much a problem. So the ratio of near infrared, so SR basically is the ratio of near infrared reflected radiant flux to red radiant flux. So basically using this equation here, note that in this chapter when we talk about this is the sign for radiant flux. So basically it's calibrated reflectors. For example, a lot of time we use Landsat to work on this kind of data. And we know that when we download Landsat data sets, usually it's calibrated and stretched from each band into value between 0 and 255. So it's like integer type. But typically when we need to use this, we need to convert it to reflectance values, which is decimal point between 0 and 1. So typically you need to first do the radiometry calibration using certain equation provided by paper, and then convert that back to the reflectance values. And then you will need to do an atmospheric correction. So after that step, what do you derive this reflectance value that we used over here? Okay, so the raw here, raw NIR refers to the reflectance value in the near infrared band, and also raw is the reflectance value in the red band. So after you did the radiometric correction and also atmospheric correction, these are the two main steps for the standard Landsat pre-processing. So after these steps, you can use this equation directly using one band, near infrared band, divided by red band. So this is a simple ratio method. And so in this majority of the test image, we're going to use this image over here. So this is the IRS image, original IRS image, and then this is simple vegetation index. So this is how they may look like. So as you can see that this kind of data set, so these blue ones will be water or those with high water concentration, and the red ones, for example, this place over here and this, yeah, those are the vegetated areas. So as you can see that it's good index to indicate where vegetation are. So it's an option. And then the other one is the reduced simple ratio, so RSR. This method is published by this paper, Chen et al. 2002, and this paper modified the simple ratio algorithm to include information from the short wavelength infrared band in the spot image. So which means that if you work with spot image, you might be able to, you have the option to use this equation here for an improved version of this simple ratio. So it's the reduced simple ratio. So, so they used this sensor to map the leaf area index. So these basically, this still here is, this left part over here is still the near infrared divided by the red reflectance band. And then right side is basically incorporate this 1 minus, and this part over here is using the shortwave. SWIR is basically shortwave infrared, and SWIR mean and SWIR max refers to the minimum value and maximum value in that band. So if you have spot image, you find that shortwave infrared band and read out the minimum value of that band, maximum value of that band, and then you can calculate this equation here. Okay, and that is like using the pixel to calculate that. So that way, and this value in the shortwave infrared is basically at every single pixel location, that's the value of that pixel in that shortwave infrared. So that way you can calculate the value at that index. Okay, so the SWIR max and SWIR mean are the minimum and maximum shortwave infrared reflectance found in each image and defined as the 1% minimum and maximum cutoff points in the histogram of short. Okay, so this is different from what I originally understand. So this is basically means that instead of taking the minimum and maximum values, you were going to read the, the histogram charts of that band may look like that. But if you take a minimum and a maximum value, sometimes that value can be very random, like quite a far or big values. But if you truncate it like a 1% on each end, and then take that value, your result will be much more more stable, because you kind of avoid those kind of random, sometimes the minimum and especially minimum value. Sometimes those extreme value can have some random effect, like they can, for example, you may have, sometimes your image may have sensor errors, and you have some pixel, just a pure white, 1 pixel like that. And then it may cause because of sensor error, so they may filtering with 255. Okay, so yeah, so in this here, in order to deal with these kind of unexpected situations, they use 1% to cut off this. Okay, so, and then the other one is most frequently used one. Like majority of the time we use NDVI, especially sometimes we calculate NDVI, like, and then throw in some other classification or some other modeling. And then majority of the time we use NDVI, so that is normalized vegetation index. So So this index is widely used, hence it's very important because it monitors seasonal and interannual changes in vegetation growth and activities. The ratioing reduces many forms of multiplicative noise present in multiple bands. So basically, like if you have atmospheric effect, for example, in the image, and then you will expect that it may exist in the near infrared band and may also have some effect in the red infrared band. So you have the upper part and divided by lower part. So hopefully this kind of equation, like the way to divide it, can in certain way cancel that effect from the atmospheric impact. Just in certain way, okay? So again, the raw here refers to the reflectance in the spectral band, which means that you need to convert that back into the reflectance value that is between 0 and 1. So this is example that showing the NDVI result of the same image over here. Okay, so the green color here illustrates those area with vegetation. Okay.
You are not using the physical value, you are using the reflectance. You are using the reflectance in the NDVI. The last two slides.
This one?
Yeah, the rule is not the pixel value. It's the band value.
It's pixel value.
Okay.
Because here, for example, for every single pixel, you will calculate NDVI value. Okay. So for example, let's say we're scanning through the image. Let's say we're looking at the first pixel of the image. And what is the value in the first pixel in that near infrared band? Put it there. And then what is the value of those red band? Put it there. Then, you put these two values in it, you calculate NDVI of that pixel. And then you repeat this for every single pixel in the image. So that's how you get this. So you only look at many of these kind of indices, you only look at any of the pixel and then just get the value from different bands. Okay. So that they do not consider the neighbor information and other things.
Areas are higher in
yeah, in this case, because you can judge that the white is representing the water, so the water is usually kind of lower value part. So obviously in this case, the green color they used in this one indicate vegetation area. Yeah. So you will see that those more highly vegetated area will have much higher vegetation index than the grass and then to the other features. Typically urban area would be the much lighter value. Yeah. So this image here shows the true color image will look like this, and the color infrared would look like this. The vegetation part will show red, but if you use this is like but if you calculate NDVI image, so it provides way to summarize multi-spectral bands into just one single band. And now you can use one single NDVI index. For example, you can use a threshold, right? For this one, for example, you can see that water is very slow, and then the vegetated area have very bright values. So you can check the histogram, and typically you may have kind of pattern like that. So the lower part you see that will represent the water. So what do you do is a lot of time you can calculate NDVI and use, for example, 0.02 or something, or 0.2 or 0.02. Anyway, so you can use a threshold to extract those vegetated area. So that's why vegetation index is quite popular. So NDVI index so widely used, but you need to be aware about some of the conditions or characteristic for this index. So the first one is the ratio-based index is nonlinear and can be influenced by additive noise effects such as the atmospheric path radiance. Okay. And then NDVI is usually highly correlated with vegetation leaf area index. So as vegetation grow in the later stage, through the cycle, for example, you think of cotton, And then when they grow bigger and bigger, and typically you will see vegetation like NDVI value increase as well. However, the relationship may not be as strong during period of maximum LAI. So this is basically refers to the phenomena over here. For example, in this table, people did the research and compare the derived simple ratio index and NDVI index, and they found this equation over here. So basically, we'll see that what this does is like in the beginning, the NDVI value increase because the y-axis here is the NDVI value, x-axis here is a simple ratio. Like this is based on different type of feature. But between simple ratio and NDVI, they have a nonlinear relationship. But what you can see that in the early stage, NDVI is increasing pretty fast, which means that NDVI is quite sensitive to the growth change. But then in the later stage, note that when it in the later part, so typically this is like we have a mathematical equation for this kind of chart. So typically for this kind of chart, we say that when it reach the higher portion of this chart, it kind of reached saturation. So which is what this one talking about, this one over here. And this is basically means that reach saturation means that when you X continue to increase, but your Y wouldn't increase much because you may be just like approaching kind of value, but not increase much. So that is one of the main problem with the NDVI. For example, last week we had one of the drone tests, and we talked with the professor who do the old study, and we're talking about checking the NDVI to monitor and check the insects, some of the rust disease in the oatmeal, and then the oat field, and then he talked about it, but NDVI will then get saturation in the high biomass stage, which means that a lot of people pretty much know that in the later stage when the NDVI like reach kind of high value, they become saturated, which means that you may see the plants continue to grow, but you do not see much change of NDVI. So once you be aware of this kind of situation, it means that we need to think about this issue and also think about other possible indices that we can use for, as a comparison to the NDVI, right? So that is what this kind of knowledge means. So that basically refers to NDVI have a kind of saturation problem in the high peak biomass, which means that in the late stage of the plant growth, once they reach the peak, and then it may have problem using NDVI for that. And also it is very sensitive to background variation. So NDVI value is known to be sensitive to background variation, especially like the soil visible through the canopy. For example, a lot of agriculture sites, they plant vegetation in a row, or in the early, especially in the early stage when the leaf area is low and you can see through and to the ground. So what kind of, like, is it all just soil, beneath your canopy, or you have a lot of underlayer grass? That all have impact on your index. So and also NDVI values are particularly high with darker canopy backgrounds. Okay, so that's kind of like a known characteristic for the NDVI values. And then the other one next one we're going to talk about tensor cap transformation. So basically, tensor cap transformation is basically refers to this method is already built in the software. So you can, when you work with Landsat image, you can directly calculate this to generate 3D. But the slides here will be helpful for you to understand what's built in internally. So basically to disaggregate the amount of soil brightness, vegetation, and moisture content in individual pixels in a Landsat MS or TM image. This is actually kind of, I think, what well, in the later slides, when we see the chart, we may talk about it. And the reason why they talk about the tassel cap is because in the tassel cap, we talked about it before. When you look at a feature space, like X as red band and Y as the near infrared band, we typically saw a chart that is like a head, right? And that also is the feature space that quite similar to like you have one end with water, the other end with soil, and the other end with the vegetation. So this is basically built based on that characteristic. So here the three index, one is called soil brightness index, which is B, and then greenness vegetation index, which is G, and yellow stuff index. So this is the method introduced by this paper in 1976. So in the early stage, remember Landsat mission is first launched in 1972. So this method is designed for MS Landsat early mission MSS dataset. So basically B here, let's take a look. So B here, we have a couple of coefficients, this number here. So SS1 means the spectral band 1, MS2, MS3, and 4. So basically using these 4 bands, but giving different weights, okay? So that's how they calculate B. And G, and it's also the same thing, just the index and the equation is different. For example, these first two are negative, and the Y is like this. So for method like this, if there's no method built in, then you can use modular builder to, like both ERDAS and ArcGIS have model builder that you can build your own equation. So you can easily build a model like this, okay? So this is based on the early stage MS dataset. And then later, this paper in 1986 modified this and produced this method based on Landsat TM. And this is the one that is used more often because the Landsat TM data is more, lasts quite long time. So a lot of people end up using this data more. But anyway, so if you use Landsat TM, and this is one to use to calculate the, so in this one here, one is called B, one is called G, and W is the wetness index. G is greenness. So basically brightness, B is brightness, G is greenness, and wetness. Okay, so so you just use this paper, you can find this coefficient and repeat this. So as you can see that since we're using Landsat TM here, we use band 1, 2, 3, 4, 5, 7. Remember, a lot of time work with the Landsat image, we get rid of the thermal band. So we don't see band 6 because band 6 is thermal band. So we end up using 1, 2, 3, 4, 5, and 7 for many applications. Okay. So this is the case for this BGW index. Okay. And then this example here, the upper one is brightness value. So you will see that quite often brightness value is often used to correspond to urban very well. So those really highly developed area will show much brighter index, and then graduate to, like you see that water showing the lowest values. So a lot of time people use these tassel cap. Again, it's available in the software. You just need to choose and run it. Okay, so then you look at the brightness band. So a lot of time people use this method to generate a brightness band and use this one correspond to urban, like to extract urban extent. So that's one of the application. And then the greenness band is like this one here. So you will notice that water presents pretty low values, but then some of the area in the urban area present quite low, quite dark value as well. But in this part of the city, like this part, that in the vegetated area, they show much brighter distribution. And this wetness index, on the other hand, called a wetness. So in this one, you will see that the water basically show much higher index, and then some of the previously bright urban area will show kind of dark, and then vegetation show relatively lighter values. Okay, So urban here become the one with the lowest, right? Because it's water index, okay? So that is how the band will look like. So basically, this is another option. Let's say, for example, if you want to extract the vegetation, you might be able to use this greenish band as a way to extract vegetation or indication of where it grows. Or if you want to, or you can also use wetness for some drought or other application. Okay, or maybe sometime you can use this as a wetness index and then produce water mask to mask out those areas with higher wetness. And then, so this is from this paper. This is basically the paper give you the coefficient values, because sometimes they may have like a modification of the values. But anyway, so these will be the source where you can reference to find the coefficient values for that different spectral bands. Okay.
There are 4 what are
they will still produce more bands, but the other bands kind of make a less sense. Like the data may not represent much. Just like for PCA, you may have more bands. Like basically the first few bands will contain more useful information for PCA. And then the other band will contain less and less information, basically more and more noise. So you just don't use them. But if you want, you can still check those to see whether it's useful. But majority of the time, I've seen people using this method, and majority of the time, people just discuss about the first 3 index. It's a transformation. So they will transform it kind of like a PCA, kind of like they transform it into a few new bands, but the first 3 make sense, so they name it. And the other one doesn't really, it's difficult to use, so they don't really end up discussing. And then the other one is called normalized difference moisture or water index. So basically NDMI or NDWI. So here you see that we introduce several kinds of vegetation index and also water index. A lot of time we need to work with both. For example, in our Rosal Cane wetland study, we are mostly interested in the vegetated area, but then we also look at the wetland area because wetland have a lot of water in it. So sometimes it may be helpful for us to calculate water index so that we can mask out those or water related area, because sometimes, especially those with the muddy area, like with more water in it, it sometimes can cause problem. So it's also very useful to know a couple of water index, and you have different application for this. Some of them just good to extract water area, water body. Some of them are gradually become more sensitive to the water moisture content in the vegetation, which is good for the drought study. But anyway, so in this one here, we're going to introduce the moisture index or the water index. So here, they are widely used in agriculture, forest, and hydrology to illustrate to measure the canopy water content. This refers to the water content within plant itself. For example, sometimes if you have drought distress, then you can use this to indicate that. And also study for the water stress, like especially for those precision agriculture measurement, or in those arid environments that is lack of water resource. And also measure the disturbances, because sometimes when certain disturbance, hurricane or some other event happen, they can damage the health of vegetation, and that can be measured from this type of vegetation index. So, so this equation here is basically quite similar to the vegetation index, but they are using different bands. So here is using NIR band, which is in TM data, they are band 4, and also mid-infrared. So basically they're using NIR and mid-infrared. Remember the water index is basically using red and near-infrared and red. And this one is basically replace them with the near-infrared and mid-infrared. And then it becomes the water index, okay? So, so this example is showing the true color, see color infrared image composition, and also water index, normalized water index. So you will see that some of the dry area in this agriculture field will show very low value because there's no vegetation, so it's pretty much dry. And a very high reflectance over here, which means that the soil is pretty much dry, which means that less moisture. So you will see these kind of areas showing much lower as a contrast. And so, and the other one is called perpendicular vegetation index, which is PVI. This is basically developed by this paper, Richardson and Wiegand, 1977, used a perpendicular distance to the soil line as indicator of plant development. So basically, we should quite familiar with this chart now. So typically, when you look at the red versus near infrared feature space, the chart will look like a tassel hat. So like this is the top of the hat, okay? So it kind of look like that, so we call it tassel hat. So in this kind of chart, they have a very kind of, by observing different land cover type on this chart, and we found that the lower part here is basically the more to this corner, the more to the water, and the more to this one would be more soil, and then the more to this end will be the one with high vegetation. So as a result, and then people often call this line here, called it soil line, because gradually extend to that part, it will be contain more soil, okay? And then if you, so towards this direction will be vegetation. So the design of vegetation, perpendicular vegetation index, basically measure, because we say that we found that if we vertically more towards this direction, the more it goes up, and then the more typically more vegetation index they will end up having. So according to this theory here, we typically call this perpendicular vegetation index. So for example, plants located in this area may have similar plant growth status, and the more growing up in the upper stage, probably with those ones, for example, low ones may be grass and other early stage, and then the upper one will be forest and other ones, like the one containing more reflectance from vegetation. So therefore, they developed this method to be able to measure mathematically these kind of vertical lines. And then the equation we used over here, this is used for MS data set. So the equation is using this one here is basically, for example, the ones involved is MSS band 4 and band 2. So this one here is band 4 and band 2 and band 4. So basically, once you have Landsat MS data set, you can calculate PVI using this equation here, okay? Again, the equation itself is quite simple. You can also use, I think the software should support this one as well, but if not, you can also use modular to build this equation itself. So which means that once you have input image, you can directly calculate PVI. So, and then the other one is called leaf water content index, which is LWCI. As you can see from this title over here, this indicates that this method probably, compared to other water index, probably much more sensitive to the water stress in leaves instead of just a water body and other things. So if you are studying those kind of features that especially care about the water content within the, you need the highly sensitive method, then you can use this one. So the equation over here is this one. As you can see that the equation, the unknown parameter is basically band 4 and band 5. So this is value in band E. So basically NIR TM4, which means that the method work with Landsat TM, and basically the near infrared band in band 4. And also the mid-infrared band in band 5. So that's the value for these two. And then the bottom part is basically where they have a special sign of FT. So they have TM4 FT, TM5 FT. So where FT represent the reflectance in the specified bands when leaves are at the maximum relative water content. That is defined as this equation over here. So basically, this method, although they are much more sensitive, but they do require you to have at least have some prior field measurement calibrated, which means that you need to go when they reach maximum relative water content, and then you go to the field and you cut some sample back, and then you measure this part is the field weight and minus the oven dry weight, and this one here is the turgid weight minus the oven dry weight. And then after this, multiply 100. So that is how you calculate that RWC. Okay. And then personally, I haven't used that method because the other part is kind of difficult to obtain. And then the soil adjusted vegetation index, SAVI. So as you can see from the name, this name indicates that, remember when we talk about the vegetation index, like NDVI, they talk about the background of the soil can often have problem impact on the NDVI, which means that give you the same vegetation status, but if you have different kind of, let's say one is in the wet soil and the other one is the dry soil, then that have an impact on your vegetation NDVI value, and that is kind of like introduce errors into your data set. So in this one here, this method basically tell you that they can adjust that effect, like in certain way reduce that effect in the equation. So the utility of SAVI for minimizing the soil noise inherent in the NDVI has been corrupted in many studies. So anyway, so this has been no problem. And then SAVI were able to kind of solve this problem. And the way they solve it is you use this equation here. Again, we still use this near infrared and red band. However, they introduce this L effect. So L is a canopy background adjustment factor that accounts for differential red and near infrared extinction through canopy. So in order to use it, and they also experiment and test the value and found that an L value of 0.5 in reflectance space was found to minimize soil brightness variation and eliminate the need for additional calibration for different soil, which means that you can just simplify this method by just giving L value with 0.5 value and then calculate this equation. So if you're interested in certain type of study, let's say in the early growth stage for the agriculture field, that your plants typically grow much small leaf area index, and then you basically can see more soil background, and you can use this method to see whether they are helpful. So this is example, the effect as a comparison. So this is the soil adjusted index. If you look at this index over here, like look at this one in this vegetated area, obvious agriculture field, it does show some variation within the field. So this could be something useful if that is one of the major concerns. And then the other one is called atmospherically resistant vegetation index, ARVI. So as you can see from the name, this method is basically claiming they can further reduce the atmospheric impact in vegetation index. So this SAVI was made less sensitive to atmospheric effect by normalizing the radiance in blue, red, near infrared bands, and this became this ARVI. ARVI band. So this one over here, this method does require prior correction for molecular scattering and ozone absorption of the blue, red, and near-infrared data, hence the term this raw star. So this is meaning that you need to do those kind of atmospheric correction. Unless the aerosol model is known a prior gamma, this parameter over here is normally equal to 1.0 to minimize atmospheric. So basically, unless you already have a known value for this one for that day, then typically simplify the application, you can just give the gamma here with the value of 1. So basically, in this equation over here, so they have this RB. So the RB, this raw RB star is basically calculated by using the red band minus with this omega, and then this equation here is basically blue minus red band. So involved equation would be red, blue, near infrared, and then but you need to calculate this value using this equation over here. Okay, so if we just simplify the use deep gamma as a value of 1, basically you need to calculate using these kind of 3 bands. But make sure that you do you do a very well atmospheric correction model on this. Since a lot of time, if we're talking about a method for atmospheric correction, like a really well correction, a lot of time it may require much more advanced models, and also the condition of the weather condition on the day or around the time when the image were acquired. Okay. So this will be the one for that situation. So anyway, so this is the ARVI index applied to the same area. And the other one is called soil and atmospherically resistant vegetation index. So basically SARVI. As you can see from the name, this method is basically claim that you will be able to solve both the problem from the soil and atmospheric. So enhance both these two parts comparing to the NDVI values. So this paper introduced in 1994 integrated the L function from SAVI and the blue band normalization in the ARVI to derive a soil and atmospheric resistant vegetation index that corrects for both soil and atmospheric noise. So as you can see that there is a clear path of method development. First, you have those based on the, be able to correct the soil, and the other one you have the one that be able to correct further the atmospheric effect. And naturally, this person later combine these two to see whether we can develop a method that can have effect improvement on both aspects. So the equation over here is again involve this is the near infrared band. And then this part over here, and this is the raw RB that you can calculate from the same equation in the previous method, and the L method, the error parameters. So, and then, or you can also have the modified SARVI, which use, again, this is the near infrared, and RB. So you use same method to calculate this raw RB, and then this is gamma value. So they provide 2 different options. Okay, you can. It's difficult to tell which method is better. You can just typically you can just test this method and then based on your data and check which one works well for your method. And then the next one is called aerosol-free vegetation index. So this method is published in 2001. And they found that under clear sky condition, the spectral bands centered on 1.6 and 2.1 μm are highly correlated with visible spectral bands centered on blue, green, and red. So therefore, they have one that is basically provide 2 different forms of vegetation index, aerosol-free vegetation index. One form is using 1.6 to replace the red band. So you derive this equation over here. they look pretty much like NDVI, but replace the red with the band with 1.6 μm. And then the other one is we replace that red band with a 0.66. Oh no, with a 2.1 μm band. So this is available for those data set that contain these spectral bands. I think what they were saying is this band, if you use these kind of bands, they found that these are quite similar to those. So if you use this, you can derive quite a similar vegetation index. However, the impact from atmospheric in this kind of longer wavelength band will be smaller, and therefore the impact on the vegetation index will be lower. Hence the name aerosol-free vegetation index. So under clear sky condition, they found that under clear sky conditions, the AFRI, especially that one based on 2.1 μm, results in values very similar to NVI. However, if the atmospheric column contains smoke or others, then these are very superior to NVIs, which means that if under clear sky condition, this method is quite similar to NVI. But if your data does have some aerosol problem like smoke, pollution, and volcano plumes, in this kind of condition, definitely try this method and it may be more helpful. Again, the use of this method will limit to the data set that contain this kind of band. Okay. And the other one is called Enhanced Vegetation Index, so EVI. So this method were developed for modest data sets. The modest land discipline group developed the EVI for use with the modest data set. So basically, they have a G value here, and the upper part we're basically using near infrared and red. And then, so this is a near infrared, and this is the red part, and this is the blue part. So they basically apply a couple of coefficients and L values. So the EVI is a modified NEVI. The main change will be in the lower part and also this G value over here. So EVI is a modified NVI with the soil adjustment factor L, which is over here, and two coefficients C1 and C2, with which describe the use of blue band in correction of the red band for atmospheric aerosol scattering. And the coefficients C1, C2, and L are empirically determined as 6.0, 7.5, and 1.0, which means that they did a previous study and tested and found suggest this set of data set parameters for this. And G is a gain factor that typically set to 2.5. So now let's take a look at this equation again. So G is known, and C1 is given, C2 is given, L is given. So once you have the data set, basically input these three bands, you can calculate enhanced vegetation index. Again, as you can see that a lot of these different variation for the index is particularly interest to those people who focus on vegetation study, especially for precision agriculture management, which they care about very much in the sensitivity and variation. So they found that this method has improved sensitivity to high biomass regions, which means that this could be one of the methods available to, like if you do have the saturation problem for NEVI, this could be one that is useful. And also this method has improved vegetation monitoring through a coupling of canopy background signal and reduction in atmospheric influences. Okay. Which means, let's say, for example, one of the applications, if we use our drone data, we can calculate NVI, and then we probably can use this method to calculate EVI, because when we acquire drone data in different season, different time, we may end up having different atmospheric conditions. So we, based on the theory here, we expect that this EVI might be able to solve the problem in the saturation part in the NDVI, and also probably will be much more stable comparing to the NDVI, like the impact from the atmospheric condition. So that's the EVI. And then this is the result applying this method to this same region over here. So red indicate the vegetation area. And then the other one, the next one is called Visible Atmospherically Resistant Index, VARI. So according to the name, they also enhance the atmospheric correction part. So so here it's that many resource managers would like vegetation fraction information, like for example, 60% instead of just classifying every pixel into just one. And then building upon this kind of atmospheric resistant vegetation index, scientists developed this kind of index as this one over here. So basically VARI green equal to this reflectance in green band minus red band divided by this bottom equation will be green plus red minus blue band. So the index, so if your data have green, red, and blue, you can calculate this VARI green. So the index was minimally sensitive to atmospheric effects, basically have less impact from the atmospheric effect, allowing estimation of vegetation fraction with an error of less than 10% in a widely range of atmospherically optical thickness. So it looks like this method may be able to deal with the plant fraction values. Anyway, so the VARI data set is applying to this will look like this. So in this chart, basically water you use this kind of red color and vegetation using this kind of blue color. Okay. So next one here is the normalized difference buildup index, NDVI. So we have talked about several index to calculate vegetation index and also water index or moisture index. Now we're going to introduce one for urban index. Basically, it's one that might be useful for us to extract urban distributions, because a lot of people study different urban sprawl issue, and they want to show from multi-temporal image show they need to extract the urban extent and then show how they gradually change. For example, the town of city of Las Vegas, how they gradually develop, become much bigger city. So many professionals working on urban suburban problem are interested in monitoring the spatial distribution and growth of urban built-up area. And this data set can be used for watershed runoff prediction and other planning applications. So in this case, in 2003, this paper introduced this NDVI, which equal to this equation over here. I think the upper part is minus mid-infrared TM5 minus near-infrared TM4. And then bottom one is the mid-infrared TM5 plus the near-infrared TM4. So, and then after you calculate this, you can use NDVI minus NDVI to extract this kind of built up area. I think there's a threshold you can apply to extract it. So in this case, they will recode NDVI and NDVI to 254 if the value is positive. And so like after you calculate this, and so they will recode this NDVI and NDVI to 254 if the value is positive. If negative, then will use 0.2 or 0.3 for NDVI threshold. The final output image contains only build-up and barren pixels having positive values, while other land cover have a value of 0 or negative 254. It's basically those that less than 0. The technique was reported to have a 92% accuracy. Okay, so that's a pretty good number. So anyway, so this is the method you're able to extract urban distribution. In the lab, we're going to have practice for this one. Next one is looking at the new vegetation index. So basically NVI. So this paper in 2001 excluded water vapor absorption bands in the creation of new vegetation index to improve the biomass monitoring capability of NDVI. So, so as you can see, that this is basically further improve to solve the problem in the water vapor absorption issue. So therefore, they use the bands with the 707, 777, 747, and 673 nanometer as the 3 band for the calculation. So that's the new vegetation index. Again, this method is limited to those kind of data set that have these kind of special bands. Okay. So if you work with this kind of data set, you can try this one. And then the other one is called red edge positioning determination, which is REP. So red edge is a well-known term in remote sensing for vegetation study because vegetation typically have these kind of spectral curve, like this one over here. So you have these kind of red portion, and then we know that once they reach the near infrared, they have a sharply increase to the near infrared. And these place with steep slope, they call it red edge. So the red edge is a region in the red near infrared transition zone of vegetation reflectance spectrum and marks the boundary between absorption by chlorophyll in the red visible region and scattering due to leaf internal structure in the near infrared region. So anyway, in the recent development, especially like in the multispectral band, especially for drone study, and people found that the red edge band sometimes have quite a big impact, like sensitive to certain vegetation activities. So for example, the red edge spectral band, one of the well-known multispectral band for the drone sensor, we first bought 5 spectral band. They have 1 red edge band, like RGB, red edge, and near infrared, so 5 band. And then they expanded to 10 band, but they just had another sampling in the red edge band area and also another in the near infrared. So it's still quite similar range, but more sampling, okay? So, but this is also indicating the importance in the red edge band. But anyway, let's see how they use it in this one over here. So in this method, the red edge positioning, REP, is basically calculated as the point of maximum slope, the point of maximum slope in the vegetation reflectance spectrum between red and near infrared wavelengths. So the study found that it's strongly correlated with foliar chlorophyll content and also a sensitive indicator of vegetation stress. So that is why we are interested in this kind of index. So one method is the one published by this paper, Cleaver's 1994. So using this one method over here, so you have this red edge band and 700 nanometer, 740 nanometer. This one is also 700 nanometer. Okay. In this case, the red edge band, this one over here, looks like it's not in the data set, like not in the original spectral band, but they can calculate it by using this 670 nanometer plus the mean of this 670 and 780 nanometer. Okay, so which means that given the data set with this kind of spectral band, you just use the band in 700, 740, 670, and 780. you can calculate this REP. Okay, so that is the REP method. So that's pretty much what we talk about different form of vegetation index. In the coming years, if you continue work with the remote sensing data set, you will find some of the index and tools is very useful, and you end up using many of them repeatedly. So I also provide slides to summarize all these methods in this table, like for your convenience. For example, sometime, let's say, like the question the other plant ecologists talk about the saturation problem. So I may look at this, think about, okay, which is the one that can deal with that saturation problem of NDVI, and then I can take a look at it here and see what are the ones that we need to test, right? So, and also another page over here. So we provide these 2 pages as a summary of the method that we produced, that we talk about, okay?